All right.
I'll go like one door, I think. I don't know if he has a handle.
All right. All right, folks. Well, as you know, we talked about last week. We do have a test this week. It will be on Wednesday. So there's our last review day about this. We've already reviewed for like a day and a half, so I'm not terribly stressed. We are going to review all day today. And then, so we have that test on Wednesday. The other group took it already. I haven't graded it yet, but they didn't seem like overly stressed out. I don't mean, that's always a dangerous thing to tell students. I don't mean as in, therefore, don't study or something like that. No, it sounds like the studying made them prepared. Does that make sense? They practice problems. That's what that practice test and those review exercises at the back of the chapter are for. What? They're not?
Not in my book.
You don't have the answers to those paper problems at the back of the chapter?
No.
I didn't know that.
So then I don't know if I'm right, so it's a waste of my time because I can think
well,
and really I'm just failing everything.
First off, okay, you could do problems that you had in the chapter, right? I mean, that would help. But you have the answers for all those problems in the back of the book.
You can just follow on, guys.
What did you say?
You can look at the answer on Slider.
It's not always right.
There's a website that has the answers?
Yeah.
Yeah, but it's not always right.
And it shows you how to do it too.
Well, I like that. So really, those ones that did like those review exercises on page, this is something I should know. So wait a minute, let's find this out. So if you went to like review exercises on page 458, those things are not at the back of the chapter. I mean, at the back of the book. Really?
Yeah, 458.
Yeah.
Have review exercises.
And what page are you finding the answers?
It's at the very back. It's A, maybe 114.
A 114? Okay, so yeah, I'm always having a hard time finding these in the back. Okay, so page A 114 review exercises. Okay, yes. So the kind of review exercises that are on page 458, those are in the back of the book. Okay, I was pretty sure they were. So right off the bat, there you have 124 example problems. Okay, now there is a chapter test at the back of the book, page 461. Page 461, I wouldn't be surprised if they don't. Oh no, look! Right there on page 1.
I've never been able to find this.
Yes. A114 and A116, that section right through there has all the answers. Fantastic. And like I said before, the test comes from stuff like that, okay? I don't give you literally the questions on chapter test. I change numbers and stuff like that. In the teacher's edition, it also has points to, like, it says things like, you know, problem 4 is a lot like problem 13 on page whatever back here. So sometimes it's not exactly the same as this, but I mean, it's very, very similar, okay? My notes about the test are all things like, this problem is actually very similar to the one they did on page 397 or something like that. Okay, they're not randomly chosen or something like that. They're very similar to things you already showed me that you knew how to do. Hold on just a second. Let me make sure this is not okay. All right. So, So that is a huge thing. So when somebody said that what should they be doing for the test? Practicing is a great idea. Okay. Cool. Making a review sheet is a great idea. And remember, the assignment, such as it was for today, was to make your review sheet at least for the first couple sections of the chapter, if not for the whole chapter. I mean, there's no reason not to. And I will be glad, real honored, to look at anybody's review sheet who wants to help, wants some help with that. Okay? Now, what kind of things are we putting on that review sheet? Well, think back to those first two sections that we've already reviewed. We've already reviewed the heck out of 6.1 and 6.2, law of sines and law of cosines. And remember, memorizing the law of sines and the law of cosines is not helpful. We talked about the fact that I'm working on reviewing for the teacher's examination or whatever, and even on the math teacher's examination, they give you a cheat sheet that has the law of sines and the law of cosines on there. They don't even expect the teachers to have memorized it, okay? They're messy. But making sure you know where they are and how to use them could be very good information to have on your cheat sheet. Okay? Now, also, information about common mistakes. Now, you did the homework. You know what you got, what was struggling for you. I know when I talk to different students, for example, on law of cosine. I'm sorry, this is law of sines. where you had stuff like this. I know that frequently when people said, Mr. Shark, if you come over here, the problem was, instead of having little a up here and big A down, you know, like they had written things like a over sine of little a. Well, that's not right. Your calculator will let you do it, but it has to be the length divided by the sine of the angle. Okay? By the way, just so we're clear, the big letters are the angles, the little letters are the sides facing opposite them, their length. Okay? Those are the kinds of things that will be hard to find during the test. If you freak out during the test, you're like, I don't remember which one is which, that will be a hard thing to find in the book. Well, no, it won't be that hard, but I'm giving you an example. If that's something that you're going to make mistakes about, like you made mistakes about that in the homework, that would be a great thing to have on your review sheet. If you tended to make mistakes on the homework about the differences between radians and degrees, having things like a reminder to you on your review sheet to check on that would be a great idea. Okay? I'm thinking of things the other section showed me on their review sheets, is what I'm saying here. Another thing to have on your review sheet that would be about those first two sections of the chapter. Remember, we had 3 different formulas about the area of a triangle. If you don't remember that, they were at the bottom, they were at the end of section 6.2. Let's find that so you have an actual page number and everything. There were 3 different ways to compute the area of a triangle depending on what information you had. Okay, they're at the bottom of page 416. There are 3 different ways to compute that. Putting on your review sheet at least where to find them, if not actually writing out those formulas. Here's the deal. Actually writing out the formulas in your review sheet might not be the best idea, just because what if you make a mistake with copying them down? I don't think that writing the formulas themselves, because they're kind of messy, I don't know if writing the formulas would be helpful. Now let's talk about those 3 formulas, because that should be easy points on the test. There are at least 2 problems, I believe, on the test that are, you know, find the area of a triangle kind of thing. Now, one of the 3 formulas is like what you learned in 3rd grade, 1/2 base times height. I don't think I'm telling tales out of school and giving away the secrets here. And I tell you, I am not going to ask you on the test a 1/2 base times height type question, okay? You passed 3rd grade math. You don't get points for that in this class, okay? So there's the other 2. One, I believe your book calls area of an oblique triangle, and the other one the book calls Heron's formula. Here's how you know which one to use. Heron's formula, which is the 3rd of the 3, if you have your page open to page 416, the one that's called Heron's formula, it depended only on the length of side A, the length of side B, and the length of side C. There's no angles involved in Heron's formula. So here's the dead giveaway. If you have a problem on the test that says find out the area of this triangle, and it has this length and this length and this length, it's a Heron's formula problem. Don't sit there and stare at your other different ones. If it has an angle, if the problem gives you an angle, it's the other one, the oblique triangle formula. Because that has things like cosine of big A times little b times little c or something like that in there. If you've got an angle, it's one of those. It's a dead giveaway. Now, as some students in the other section pointed out, both formulas work all the time. But you might have to do things like law of sines to mess with it. Don't do that. If I give you in one of the problems 3 of the sides, just do this and it becomes arithmetic. If I gave you one of the angles, just do this and then it's just arithmetic. Don't stress about it. These problems are meant to be easy points. Okay? So like on your review sheet, writing down that serious hint I just gave you, there won't, on area, you know, there won't be area of the triangle problems that are the grade school formula. And if you know all 3 sides, use Heron's formula, otherwise use the oblique triangle formula, is a great thing to write down. More important than writing all those formulas out. Okay? And you'll get them right. Easy points.
Formula if you know all the signs.
Yeah, Heron's formula only has the little letters in it. The little a, little b, little c. It's what you use if you only know the lengths of each of the sides. Because as the students pointed out in the other section, I can't remember if anybody put it down this one, in fact, Both formulas work for any triangle. You just might have to use law of sines to figure out one of the angles first, or you might have to use law of cosines to figure out one of the sides first. But that's like tripling the work. Don't do that to yourself on the test. All right. Let's move forward and talk about the second half of that chapter. Second half of the chapter started off with vectors. One whole easy thing. It's so easy it's hard to believe you're going to get college credit for doing this, is the business of adding vectors. Remember, hey, let's be clear about this here. Here's a vector. And he's got something, comma, something. Like 4, comma, 3. Okay? That's our vector. Hey, that vector has... We could draw him. Now, when we only have one endpoint, see, you just have something, comma, something. That's one point on the piece of graph paper there. This vector is that is the ending point of this vector. 1, 2, 3, 4. 1, 2, 3. He's right here. That's the ending point of the vector. 4, comma, 3. What's the starting point of this vector? If you only have one point that describes the vector, the other point, the beginning point of the vector, is the origin. That's called standard form. When a vector is written in standard form, that means we are assuming that the start of the vector is at the origin, excuse me, the hiccups, and the ending point of the vector is with the coordinates that you were given. Your book spends some time on the other form as well. Where like, here's some point, I'm going to use the same symbol the book did, P, and here's some other point, Q, and we had a vector PQ. Allow me to be super kind to you. I'm going to pull out a copy of the test. Let me just look. I don't think I ever did that to you on the test. Yeah, okay. This way of writing vectors never happened on the test. Okay? Because I did some flipping through like physics textbooks, engineering textbooks, etc. And here's the deal. After introducing that such a thing as possible, they never do it again. They always write the vectors in standard form. So I was like, what's the point of... I mean, we only did it on like a handful of problems. And other books are never going to do it. So, hey, so all the vectors we write are in standard form. Great. It's a vector. Vectors always can be described as having a length and a direction. Hey, we don't use the word length when we're talking about vectors. At least we kind of formally do. We should. The right word is the magnitude. The magnitude of this vector. And do you remember how we wrote the magnitude of a vector? What's the symbol that we used in this book? It was kind of like that double absolute value thing. I can't say I'm really familiar with that symbol. That doesn't strike me as something we use in other textbooks, but if it's what this book is using, I can live with that. And that magnitude, the length of that vector, in this case would just be the square root of 4 squared plus 3 squared. It's this number squared plus this number squared. That's its magnitude. Its direction, if we were to describe its direction as this little angle right here, we could get that little angle as the tangent of that angle is equal to this number divided by this number, 3 over 4. Because, you know, it's opposite over adjacent, SOHCAHTOA kind of thing. Oh, wait a minute, wait a minute, wait a minute. Now what? If I had a problem on the test that said, what is the value of that theta? What is that angle? How would you get it? You've got the tangent of theta is 3/4. How are you going to get the angle? Inverse tangent. Remember, anytime you've got like that, a trig function of some angle, sine of this, cosine of this, tangent of this, whatever, how you bust this out is to take the inverse function of it, inverse tangent in this case, of tangent of theta, equals inverse tangent of that number. Because these guys cancel out. And then it's just calculator work. That could be a very valuable thing to have on your review sheet. Because here's the deal. We've been doing that since like January, and it's very easy for that to be something that you don't remember when you get to the test, and that would be a hard thing to find in your book when you're panicking. So having some information on your review sheet that says anytime you've got like sine of theta equals some number, and you're trying to find the theta, just use the inverse function. Because then you get to get rid of this if you just have theta equals, and this is just calculator work. I'm watching my messages very closely today. Were you guys in on the loop about my naughty 5-year-old? He's been very bad at school. The other day he instigated a food fight.
Yes.
And that's like just the beginning. And so he's been over there for a grand total of about 45 minutes now. And I fully expected the message of, come pick up your child. You know what I'm saying? Anyway, because he was very naughty last week or so. Anyway, they have to try. Ask your parents. You went through phases.
I don't know that
I bet you did other things. Did you pull hair?
No.
Did you push kids down?
I was a bad kid.
I wasn't
perfect.
I
wasn't
was
there long
in
enough to do it.
What did you say?
I was like in the office Trig fighting.
Yeah, we got lucky. We had half day. We were the last
Yeah.
like class that had half days.
When you threw your shoe at Maya.
Yeah.
So we didn't really have enough time to do anything.
Oh,
You
man.
guys were tripping.
I think the worst thing my mom got a call for was I would like refuse to eat my lunch or something.
Oh, okay.
I would talk too much.
I believe you, because you guys are all good kids.
No,
my kid menace to society right now. Anyway, I'm just telling you, you threw an orange at a kid. Anyway,
I got like car chases every day for talking too much. So like, I'm not calling home.
there you go. Anyway, so yeah, I'm watching my messages because I'm quite sure there's going to be a come pick up your little felon. All right, anyway. All right, so that's a good thing to have on your review sheet. Okay? If that's something you're worried your brain is going to forget, because I know I could do that myself, is forget that day, that would be the kind of thing to have on the review sheet. But you know what? Once you have that, the rest of the vector thing, that first day of vectors, that 6.3 rather, it's almost embarrassing that you're going to get college credit for it. I mean, a lot of those problems are awfully darn easy. I mean, there's going to be something on there like this. I mean, remember, we did things like add vectors or at scale vectors by doing the scalar multiplication. So there are problems on the test like, if I give you u and v like this, tell me what is u plus v. It's almost embarrassing that you get such easy, I mean, the vector u and the vector v, all we do is we add the first coordinates, 4 plus 1 is 5, comma, we add the second coordinates. I mean, graphically, all that is we're taking that first vector, 1, 2, 3, 4, 1, 2, 3. Here's, well, I'm doing this v plus u, but whatever. There's v. And then we add u to it by like putting the tail of the u and going one step down the x direction, one step down the y direction. Here we go. We're just adding the two together. It's that simple. And you don't even have to do the graphing of this on the test. Same with, like, for example, it's almost embarrassing that you get college credit for that, for adding those two guys together like that. All right? Or there are problems on the test that are things like 3 times v. Well, remember, this is a scalar. Scalar is the right word just for like a real number, but it scales the vector. So this will just be a vector in the same direction as v, but 3 times longer. It'll be 3 times the quantity, 4 comma 3. So it'll be 4 times 3, which is 12, comma 3 times 3 is 9. It's just a vector in the same direction as v, but 3 times as long. If it had been negative 1 times v, it would be a vector the same length as v, just in the opposite direction as v. these are not so bad. And you know what? It actually adds up to a fair number of points of the test. I mean, I don't know, there's like 40 points on the test and you get like 7 of them or something from problems like that. Oh my gosh. No reason to get any of those wrong. Hey, we were talking earlier about the length of vector v. What if the length of that vector had happened, you did the math and it works out to 1. We have a special word for vectors whose length is 1. Do you remember what it is?
Unit vector.
Unit vector, exactly. A unit vector is a vector in any direction, doesn't really matter which direction you're pointing, who has a length of 1. In practice, you can take any old vector you want and find a unit vector in its direction. I mean, we could take this v over here, whose length we found before. I mean, we found its length, 4 squared plus 3 squared. Let's see, 16 plus 9 is 25. Square root of 25 is 5. We could say, what would be a unit vector in that direction? In the direction of 4 comma 3. I mean, it's going to be some little stubby vector sitting right over here someplace. We actually, the book didn't use that notation, but anytime you have a little caret above, it's technically called the hat, on top of a vector, that means it's a unit vector. So what was the unit vector in the direction of v? The unit vector in the direction of v would just be that 1 over the length of the original vector times the original vector. So this would be 1/5 times your original vector, 4 comma 3, which works out to 4/5 comma 3/5. In and of itself, that's interesting and kind of important in a few applications here and there. It's called natural coordinates, but we're not doing, the book doesn't even have the word natural coordinates in the index. There are relatively few applications, though, where you do that. On the other hand, there are unit vectors that are super important. Those unit vectors that are super important were I hat and j hat. I hat and j hat. Where I hat was a unit vector along the x direction, and j hat is a unit vector pointing in the y direction. Let's be clear. I hat and j hat are vectors. I can even write out what they are. I hat is 1 comma 0. It has a length of 1 and it's just going in the x direction. J hat is 0 comma 1. It has a length of 1 and it goes in the y direction. Why do we do this? Well, this is called the standard basis, and there's a million great applications for this and so on, all of which your book puts off to another day. But your book does do things like this. V equals 4I hat plus 3J hat. Remember, your book gets a little sloppy and doesn't always put the hats on there. Sometimes they just write it with bold. I will not be sloppy on the test. The hat's always there. Now, you could go ahead and figure out what that means for V. I mean, if that means 4 times I hat is 1 comma 0, plus 3 times j hat, where j hat is 1 comma 3. Well, that's just scalar multiplication. 4 comma 0 plus 3, 0 comma 3. And then that's just vector addition. That's just 4 comma 3. Or you could have just noticed, wait a minute, it's 4, 3. 4, 3. And that would have been fine. Here's the deal. You're never going to be in trouble on this test if you just did that. Okay? I'm not like expecting you to go through all these little steps that I just did right here. Why did I just show them? Because sometimes people freak out and they're going to want to do that. And I want to show you that you're not doing anything wrong, you're just taking extra steps. Okay? But so this business of writing them out this way turns out to be Just another way of writing 4 comma 3. 4I plus 3j is the same thing as 4 comma 3. And that's all we did in section 6.3. If I were trying to make a review sheet about section 6.3, I might write myself out that formula for how to compute the length of a vector, the magnitude, that's in a blue box with yellow highlighting on page 421, but I wouldn't go nuts. On page 421, notice they have a lot of time on that box spent on that whole PQ vector notation that we aren't even going to have on the test. So having on your review sheet that, like, if your vector, this is not a good thing, if your vector is a comma b, then the magnitude of v is the square root of a squared plus b squared. That would be a good thing to have because, frankly, it's kind of messy in the book. But other than that, I don't know that I'd get all that stressed. Let's see what else we had on that section. Well, you know, on page 423, we had a big list of those properties of vector addition. Honestly, I don't know any of that shows up on the test. I mean, most of those rules were kind of what you would expect. Things like u plus v equals v plus u. Yes. What is that, a commutative property? I can't even remember the ranking for that. Another one was like the distributive property and so on. I don't care. Okay? Actually, like later in life in math class, upper division math classes, that would matter, but here I don't care that much. Alright. And then we're done with that chapter. Not that chapter, that section rather. Then I moved on to section 6.4. And there was one super important thing to understand in section 6.4. And that was this idea of the dot product. The dot product is one of the ways to multiply vectors. Another was that scalar multiplication. There are others as well. But like if I had some vector A, who was, let's say, A1, comma, A2, and I had some vector B, who had two numbers, we'll call them B1 and B2, the dot product is one thing you can do with two vectors. All you do is you multiply the first coordinates times each other, plus, and then you multiply the second coordinates times each other. So like if my A was 3, 4, and my B was -1, 7, my dot product would be 3 times -1 is -3, plus 4 times 7 is 28, which will be -3 plus 28 is 25. Notice, the dot product, it's just a number. You take two vectors and you get a number. There are problems on the test where I give you A is this, B is that, with dot product. You get points for that. That's awesome. Alright, I'm expecting everybody to get that right. I did this problem on the review session with the other section and they freaked out a little bit. Let's say A was equal to this thing here. What is A dot I hat? Well, that could be then 3, 4 dot, and I hat is 1, 0. So it's 3 times 1 is 3, plus 4 times 0 is 0 equals 3. It's easy to forget that I hat and j hat are vectors, and you can do all the vectory things like add them and dot them and all that kind of stuff too. I don't know that any of those showed up on the final version of the test, but they certainly were in some of the drafts. Okay. What was that dot product? Well, that's a little bit complicated. It is a measure of to what extent the two vectors are in the same direction. If the two vectors are perpendicular to each other, a better word is orthogonal to each other, then the dot product is 0. In fact, that was a thing. We had a bunch of problems on the homework where they said, take these two vectors and tell me if they're perpendicular to each other. And so you said, hey, are A and B perpendicular to each other? I don't know. So I'll take A dot B, do the math, and oh, I got a number. And since it's not zero, they are not perpendicular to each other. That's really easy. Your book then made that much more difficult by saying, they gave you A, find a vector B that was perpendicular. We are not doing that on the test. So if the two vectors are perpendicular to each other, the dot product will be 0. If they're in the same direction, the number will be big. You know, so it'll be like a small positive number, smaller, bigger, 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 getting bigger and bigger. If they were in the exact same direction, it gets even bigger and bigger, but we're not going to go into like, well, how big is big and all that kind of stuff. If the vectors are in the opposite direction, it's a big negative number. So it goes from 0 to a little negative number to a big negative number if they're opposite each other. You can actually figure out that angle between the two of them using the dot product. If you've got two vectors, one's off this way and one's off this way, and you know their coordinates there, you can find this angle between them using the formula on page 435, where it says the cosine of that angle will be equal to u dot v over the magnitude of u times the magnitude of v. I would definitely highlight that on my review sheet. Hint, hint. I am subtle today. Definitely have that on there. So if you had two vectors, you could find the angle between them pretty darn easy. Let's do that. Let's say, here we go. V is 4, 3, and U is 6, 4. I want to know the angle between these two. Alright, I'm going to need to know the numerator of this is U dot V. So the numerator of this will be 6 times 4 is 24, plus 4 times 3 is 12, over, we need the magnitude of U and the magnitude of V. I should have chosen around more ones that were easier, but what the heck. What's the magnitude of each of these guys? 4 squared plus 3 squared is 25. This one's going to have a magnitude of 5. 36 plus 16, right, this squared plus this squared is square root of 40. All right, 36 plus 16, no, square root of 50. Which is 5 times the square root of 2, all right? 36 plus 16 is 50. Square root of 50 is the square root of 2. Okay. All right. So this is going to be 5 times the square root of 2 times 5, or whatever. So this is going to be 36 divided by 25 times the square root of 2. There. What is 36 divided by the quantity 25 times the square root of 2? You don't know how to do it. It'll be something called number. And then you'll just use your inverse cosine trick to find out what the angle is. Sometimes Google's assistant doesn't understand what to do with the parentheses in an equation. Alright. Definitely be able to do that. What you don't have any on the test of is projection. Here's the deal. I'm not sure I'm thrilled with the way it explained projection in that book, and I'm not thrilled with the way I tried to improve it. I don't think the projection questions would go well, and I don't think that's your fault. Here's something else that won't be on the test. The rest of that chapter, remember, is about work. As in the concept of work, like as in from physics, like force, energy, work, those kinds of things that you probably had in like a 7th grade science class. Here's the deal. In your 7th grade science class, you had a better explanation of the idea of work than what's in this book. Okay? This book was clearly a math teacher trying to explain something he learned in 7th grade, and it just didn't work. Okay? If you remember anything about 7th grade physics where you were launching potatoes with a potato cannon and all that kind of stuff, you remember more about how work works and stuff like that this book gives. I don't want to mess any of that up if it's still in your head. Therefore, we are not touching that part of the book. It's just not a good explanation. Make sense? So basically, dot product and what you can do with dot products in terms of measuring angles is all I can give you from section 6.4. Okay? Then you turn the page to section 6.5. And 6.5 was about relating these ideas to the ideas of complex numbers. Okay, complex numbers. Complex numbers, you mean stuff like, hold on. So here's some complex number, we'll call it Z. It's A plus B times I. Complex numbers are numbers. That is really hard to think about. Complex numbers are numbers. They're not less like a number than 3 is. Okay? Anything you can do with numbers, you can do with complex numbers. Like add them, multiply them, divide them, scale vectors by them, and so on. The last one, which is terrifying, we didn't do in the class, but you can. But they are numbers. When you were in grade school, you learned about numbers as in a place on the number line. Mrs. second grade teacher told you to plot 3, and you went 1, 2, 3 down the number line and said that spot on that number line is 3. And -2 is this spot over here on the number line. All you've done different with complex numbers is said it can be in 2 dimensions. So like, if my complex number is 3 plus 4i, that means I went 3 down the real axis, and 4 down the imaginary axis, and this spot right here is Z. They are numbers. It's hard to think about this. It's hard for math majors in college to think about this. It's hard for physics majors to think about this. It's hard for engineering majors to think about it, but they are important. And fortunately, they're not really all that hard to work with. All the nifty things that we loved doing with numbers, like adding them and subtracting them and multiplying them, we can do. But that's not, we did that back in pre-calculus, right? If we had that some complex number was 4 plus 3i. Hey, what was that I again? What was that thing? What was I equal to? Square root of -1? Which is a hard thing to think about. In grade school you learned you couldn't take square roots of negative numbers. You put them in your calculator, it gives you errors. It gives you error because it isn't something you can write on the calculator screen. Doesn't mean that there isn't such a thing as the square root of -1. It just means we can't write it out. Okay. But we can do all those things like add them together. If I wanted to take this complex number and add it to this one, all I do is add the real parts and add the imaginary parts, and I'm done. It kind of works like adding vectors, which is why it's in this chapter. And your book likes talking in this chapter about things like, we could describe this guy in terms of his length. We use the symbol r here, out to where he is, and we could use this angle theta. This would be another way to write out the complex number. We like to write them out in that a plus bi type form, like 3 plus 4i. In fact, we like it so much that we gave it a name, the standard form. But that is not always the best way to write a complex number. For certain purposes, writing the complex number out in this other way, where we have r, the length it is, wait a minute, this length from where it is at the origin out to that complex number, that r, which is also written as the absolute value of that complex number. Remember that term? Absolute value. You learned about absolute value back in grade school. What is the absolute value of -4? And you diligently wrote down 4, and you learned something. Probably in grade school they just said it's the same as the number unless it's negative, and then you just change it from negative to positive. A better way of thinking about absolute value is how far r is your number from the origin. When you learned What is the absolute value of negative 2? And it was 2. What they mean is you are 2 from the origin. So what is the absolute value of this number here? It's just how far you are from the origin. So like if your number was a plus bi, it's just a squared plus b squared. And if you're thinking that looked a lot like the that looked like the magnitude of a vector, you're right. That's why it's in this chapter. There's another word for this, by the way. This is called the absolute value of the complex number v. A complex number z, or called the modulus of z. I'm not sure why there's two terms for that. I tell you that because I believe I use both terms on the test. I know, I definitely remember when I had a draft of the test, I looked through and went, I've noticed I'm calling it the modulus in one place and the absolute value in another. I don't remember if I fixed that. Well, not fixed it, or decided that was a good thing that you knew two terms for it. I can't remember what I did. But it turns out if you have that absolute value, or that modulus of your complex number, and you have this angle here, which, I mean, if this is a plus bi, that is just the tangent of b over a. And we use our trig to bust that out of there. Turns out once you've got that, another way to write that same complex number is r times the quantity of the cosine of theta plus I times the sine of theta. This and this thing are the same. There are two different ways of writing the same complex number. One of them, the standard form, is go a steps down the real axis and b steps down the imaginary axis. That's where you are. That's your point. The other one says turn theta this way and then go r steps that direction. But they're both ways of saying the same complex number. They're just two different ways to get there. Why? Why are we doing this? Because it turns out some things you can do with complex numbers are easier to do and easier to understand if they are written in the trig form instead of in the standard form. Some things are really hard to figure out how to do in the standard form. Or it's really hard to figure out what they mean. And in your book, the main thing we dwelled on was the idea of how to do multiplication. I mean, this is just a number. I'll call this Z1. Here's another number. I'll call it Z2. We should be able to multiply these numbers. The mere fact that they are complex numbers has literally nothing to do with it. Just as much as you can multiply 3 times 4 on the number line, you can multiply Z1 and Z2. But it's hard to think about. Now back in pre-calculus, we did multiply them out by using FOIL, and we were not happy about it. Because there's nothing about that FOIL trick. Oh, FOIL's easy. But there was nothing about FOIL that helped us understand what this even was. What did it mean to multiply two complex numbers together? On the other hand, if you have these two guys in trig form, like if you had this Z1 was equal to R1 times the cosine of theta 1 plus I times the sine of theta 1, and you had this Z2 was equal to Z2 times the cosine of theta, the cosine of theta 2 plus I times the sine of theta 2. You have them written in the trig form. Multiplying them is ridiculously easy. It's R1 times R2 times the cosine of theta 1 plus theta 2 plus I times the sine of the sum of those angles. Now, you're saying, no, 1,000 times no. I'd rather get it wrong than study that. I've been there. But don't get it wrong. It's easy. It's in the book. Let me show you. Go to page 446, and in a blue box with yellow highlighting, they have that formula. Do not write that formula down, but point it to on your review sheet that says, if he has me multiplying two complex numbers, that's the formula to do it. And it's not really all that hard because look, these are just, all we did is add two angles. So if theta 1 was, I don't know, let's just say theta 1 was 17 degrees, and theta 2 was 73 degrees. That looks horrible, but here's the deal. What is theta 1 plus theta 2 here? 90. So cosine of 90 plus I times the sine of 90. They will always be problems where when you add the two thetas together, you get really round numbers. Like 90 degrees, or 45 degrees, or 180 degrees. Where things like sine and cosine are so easy, you can do them in your head. Or look at the unit circle in the front of your book, or whatever. I'm saying there will always be. The word they there implies that there's more than one of these problems. I don't think there is. But if you had two angles here, two complex numbers here, multiplying them is pretty darn simple. And in fact, it has a very nice graphical idea. Like, here's angle theta 1, here's angle theta 2, and wherever z1 times z2 is, it's just this angle plus this angle to give you this angle. Something FOIL gave you no clue about. FOIL didn't help this at all. Back when we did that in pre-calculus. You didn't like this back in pre-calculus because you couldn't figure out what any of it meant. Now you can see, look, I'm still a little unclear what the whole multiplying of complex numbers is, but I can at least see graphically, whatever angle was pointing toward the first one, whatever angle was pointing toward the second one, the product of them, it just added those angles up. There won't be a problem on the test that involves division of complex numbers. Not that division is harder, or something like that. It's in that same blue box on page 448 or 446, whatever it is. But here's the deal. You don't have all day to take the test. And do you demonstrate anything by doing the division that you didn't already know how to do for the multiplication? It's just the same equation, except there's minus signs in it instead of divided by 2. So here's the deal. It would be a waste of your time. If you could do one, you could do the other. So I chose, there's only a multiplication one on there. Now, many students said, what about the rest of section 6.5, which has de Moivre's formula? And they said, I think you were going to tell us about de Moivre, and then you didn't, and so on. De Moivre's formula is about powers. If complex numbers are just numbers, if I could take a number like 3, and I can square it, can I take a number like z1 and square it? Can I say, hey, if that's z1, a complex number, can I square it? Well, sure you can. It's the same thing as saying z1 times z1. And then the de Moivre's formula shows you how you would use that multiplication of two complex numbers to just do z1 times z1, and you get de Moivre's formula. Here's the deal. We're not going to do that on the test. Again, after looking through the teacher's information and so on, and the assessment stuff for the class and so on, I was like, well, then what did you demonstrate from de Moivre that you didn't already know from how to multiply complex numbers? All it does is it shows you how, then what about z cubed? Well, it would be z1 times z1, and then you do it again. But it's just the same thing over and over again. It isn't really showing that you know anything different, right? So, although there are many cool things and cool applications, from how the antenna works on your cell phone, to how waves move through the atmosphere, to have all kinds of engineering applications and so on, to de Moivre, your book never goes there. I can't test you on things the book didn't do. And de Moivre is really, in many ways, just the multiplication of complex numbers just done again and again. You've already demonstrated that on the test. There's no point in testing that. Same with, if on the facing page, there's something there about radicals, like what is the square root? If I can have the square root of 3, can't I have the square root of z? I mean, if complex numbers are just numbers, shouldn't roots work? And in fact, yes, they do, and it shows you how to do it. But again, it's kind of just the same thing again, right? So we're not going to do roots of complex numbers either on the test. The test was long enough, and in many ways that was just asking you the same thing again and again. And I don't want to do that on the test. So, test exists. Other sections already taken it. They took it on Friday. It is 5 pieces of paper. Here, I'll even stand far enough away that you can't read it. Test. See, oh look, there's a multiple choice type problem there. Hey, there's a multiple choice problem right there. There's some white space here where you do some math. Trig left this. I can't believe I just said that there's a place there for you to do some math. Look, here's a multiple choice question. Here's some place where you can do some math. Here's a whole list of little tiny problems of which you can't guess what that list is. Right? I think that might be like adding vectors and subtract, like I gave you some vectors here and you have to add them or dot product them or something like that, or find the angle between them or something like that. Let me tell you about one thing. One thing that is on the test, it's only worth 2 points. But on a test with 40 points, 2 points, you know, that could be the difference between like getting a 98 and getting a 95 on the test, right? Could be. Is I want you to be clear about one thing that we use the same letter for 2 places in this chapter. And that was the letter I. You know, we had vectors where we use the letter I. Like we had V equals 3I hat plus 4J hat. And we had complex numbers where we had things like Z equals 3 plus 4I. Did you notice in the course of this chapter that we had used I like that? That there were 2 different ways we were using I. I want you to be clear on the test. There is a question worth 2 points where you have to be clear as to which one is which. Okay? In vectors, this I hat is a unit vector in the x direction. And that is not the same thing as I is equal to the square root of -1. Okay? This is just a number, admittedly an imaginary number. Remember, the word imaginary here doesn't mean as in it's not a thing that is, I don't want to use the word real because real is a type of number too. But, I mean, it's just a number. Square root of -1 is a number. Not a number that you can point to on the number line, but a number. I hat has nothing to do with it. I hat, which again your book sloppily just writes I about half the time, is a vector. Okay, there is a problem on the test worth 2 points where you had to be clear about that. Okay, where it would be easy if you didn't realize there was a difference here, you could fall into a trap. Someplace along the way it said, like in the teacher's guides and stuff like that, make sure your students know the difference between I and I hat. Okay, and I want to make sure. Okay. Most of the students on Friday when they took the test took just about the whole period. Okay, that can be scary. On the other hand, it did look to me, just kind of like trying not to snoop, but also kind of snooping and getting a sense of what's going on. It looked to me like they got most of the test done in like the first 20 minutes, and then they were sort of, you know, like, oh man, that whole multiplying 2 complex numbers, I can't remember how to do that, and they're flipping through the book, and they're flipping through their notes, and they're fighting and fighting and fighting for a 3-point question. Does that make sense? I mean, don't get me wrong, I don't mean that in a bad way. I mean that as in, they probably had 95% of the points they're going to get in the first 20 minutes. You know what I'm saying? I mean, it isn't like the test, and then they were just like, well, what else am I going to sit here for the next might as well try to figure out what I'm doing. Try to get those last couple points. I have not graded theirs though yet. For all I know, it went horribly wrong. No, I don't think it did. I don't think, again, you have pretty obvious guesses as to what the problem is going to be. Law of sines, law of cosines. Oh, let's be clear about that here. I do explicitly say, here, I don't think I'm giving away anything just to ignore here. I mean, like on problem B right here, use law of sines to solve this triangle in this problem. Notice I explicitly tell you which one it is. Here we go. Use law of sines to solve this problem. Solve this problem using law of cosines. Hey, remember when we did the law of sines, there was the possibility that sometimes there was 0 solutions, sometimes there was 1, and sometimes there was 2. Any problem where it says using the law of sines, it is a 1 solution type thing. I don't want you doing the thing where you have to do twice as much work trying to find the 2 different solutions. But there is a problem that says, hey, this is a law of sines problem, here's the information, here's an angle and a side and a side. Angle and a side and a side. This problem sounds like a pain in the, right? And then you have to use that technique that you have in your book there to figure out, does it have A, no solutions, B, 1 solution, C, 2 solutions. Right? So you just use those rules. What page is that? 416 or something like that? Arrow, because that would be a good thing to have on your review sheet. 406. 406. Okay, I was close. Page 406, that little table right there. So there is 1 2-point problem where you got to do that. Remember, our goal is to do well the first time on the test this time. Okay? That way, yes, we still are going to do the getting points back thing, but I want you to be, it's more like the polishing your shoes step. You've got a great score, you just want it to get even a little better. Yes, if it doesn't go great, then it's also about, fixing that. But I want it to be more like how we polish things up. Make sense? Fantastic! All right, I'm going to turn off the camera.